So probability of error. So I have phi x and phi y, my filter outputs with noise. So let's redraw my hardware model. Noise comes in, I do A to D. On the other side of the noise, oops, I have my two filters and my decision device. So this filter dots with SX, and this filter dots with SY. And I'm going to say that this filter output is phi X, and this filter output is phi Y. What I have is that phi X is distributed Gaussian with mean alpha I and variance N0-2TS. And phi Y is distributed Gaussian with mean beta I and variance N0-2TS. That's given I was sent. Symbol I was sent. Okay, so that's nice. What I don't know is I don't yet know whether these are independent. So if I don't know that they're independent, I have to write their probability density jointly. They're random variables that occur simultaneously, and we have reason to believe that they might be dependent because the noise is added here, and this is basically signal processing on the same noise. So they're related in the sense that I added the noise over here, and the signal processing I'm doing is all in the same noise vector. So it stands to reason that they might not be independent. So my joint probability density function is this, f of xi and f of phi x and phi y, given that I was sent. So remember, I have my Voronoi region VI corresponding to the IF symbol. VI is the set of all points that's closest in signal space to signal I. So what I can do is I can integrate over VI d phi x, d phi y. If I integrate over VI, what am I doing? I'm basically saying, if my point lands in VI, then I'm deciding that I occurred. So what, physically speaking, what would this be?
The area of the region.
It's the area, it's the probability weight of the Voronoi region. But if my point lands in the Voronoi region, am I making the right decision or the wrong decision?
Correct.
I'm making the correct decision. So this is the probability of the correct decision. How would I get the probability of error? 1 minus. Okay. Are these independent? If they are, we can split this into two Gaussian probability density functions. We know how to deal with those. It turns out, I will not show this, it's not too hard to show, but it turns out that they are independent if these two basis functions, these two filters, are orthogonal. So it's yes if Sx dot Sy equals 0. So in some sense, you could say in signal space, I have noise, I have one Gaussian noise vector going in this direction and one Gaussian noise vector going in this direction, and these two directions are independent of each other. So I won't show that, but we'll just take it for granted. Okay, so I now have that these are, since Sx and Xy and Sy are in fact orthogonal, I integrate over the Voronoi region. This now separates into f of phi x given I times f of phi y given I. d phi x, d phi y. Okay. If the Voronoi region looks funny like this or something, then this is as simple as it gets. But if the Voronoi region is rectangular like this, then we can simplify. So let's say by rectangular I mean in the x direction limited between x min and x max, and in the y direction limited by y min and y max. So if that's true, then my integrals are now from phi x equals x min to x max, and phi y equals y min to y max. Now, this integral doesn't depend on y, so I can take this term out, and basically what I can do is I can separate the two integrals. So I get 1 minus integral phi x from x min to x max f of phi x given I d phi x times the integral from phi y equals y min to y max f of phi y given I d phi y. So that's great. What I've done is I've taken this complicated expression and separated it into a Gaussian integral from x min to x max, and another Gaussian integral from y min to y max. And we know how to deal with those. So, as one example, let's take this. Integral from phi x equals x min to x max. Well, let's draw out my Gaussian. So this is the Gaussian with mean alpha I and some variance. And basically what I want is the integral from x min to x max. So I want this. But what we're more accustomed to dealing with is this. We're more accustomed to dealing with these kinds of problems. Getting the weights of the tails rather than the weights of the middle. Actually, they're related by 1 minus these weights equal to that. So we know how to solve this kind of problem using first C. So we just take 1 minus that, and we have the solution for this.